Hi everyone, I'm Arpit, and I'll be talking about learning with limited rounds of adaptivity. This is joint work with my advisors Shivani Agarwal, Safera Sadi, and Sanjeev Khanna. We look at the following problem. There is a collection of coins, and each coin has a hidden bias. However, we are given access to an oracle that can toss any given coin for us. Now, the goal is to design an algorithm that can identify the k most biased coins by tossing these coins and observing the outcome. You can also think of these coins as arms in Bernoulli bandits. The parameter for this problem are n, which is the number of coins in our collection, k, which is the target number of coins, which is a number from 1 to n, and delta k, which is the gap parameter. It is the difference between the k and the k plus 1th largest biases. Now, previous algorithms for this problem work in a fully adaptive framework. In this framework, the algorithm asks a query to the coin toss oracle, and the oracle responds with an answer. Here, the query Q1 is the index is an index of a coin, and the answer is either heads or tails. And 1 indicates this is one round of interaction. Now, based on the answer, the algorithm adapts and asks another query, and the oracle again responds. And this goes on for some number of rounds until the time the algorithm is confident enough that it has identified the k most biased coins, and it outputs. The query complexity, or sometimes also called sample complexity, is the number of coins tossed. Okay. Now note that each query is adaptively chosen based on all the previous answers, and hence the name full adaptivity. Now, it is very nice to have full adaptivity, but it is unreasonable in a lot of applications. Consider following simple problem in crop selection. We have 100 different crops, 100 different varieties of a single crop, and we want to identify the 2 best crops based on the average produce. Now, testing or querying a single crop takes one entire season, and it is unreasonable to wait for one entire season to test another crop. In general, in these applications, executing one query takes a lot of time. So a natural solution is to parallelize the execution of these queries. But if we parallelize the execution, we will lose full adaptivity. Hence, we introduce this framework of limited adaptivity in the context of adaptive algorithms. In this framework, an R-round adaptive algorithm asks a bunch of queries in parallel to the oracle, and the oracle responds to these queries simultaneously. Based on these responses, the algorithm adapts and asks another set of queries in parallel. And this goes on for R rounds, after which the algorithm is confident that it has identified the k most biased coins. Now, 2 things about this setting. The number of queries asked in each round need not be the same, and one query can be asked multiple times in a single round. Okay. The query complexity is the number of coins tossed, and the round complexity is the number of round of interaction the algorithm uses. Okay. Now, it is obvious that the query complexity of any R round algorithm for any R would be at least as of the best R round algorithm for any R would be at least as much as the query complexity of the best fully adaptive algorithm, because full adaptivity has more power. Now, the question we ask is that can we do as well in terms of query complexity as the best fully adaptive algorithm in this framework by using very few rounds of parallel interaction. Okay. More formally, our goal is to design an algorithm for this problem that not only has optimal query complexity, but also optimal round complexity. And note that in this work, we are only focusing on worst case optimality. We will talk a bit about instance-wise optimality in the end. Another question that we would like to understand is that if we are only given 2 rounds of interaction, what is the best query complexity that we can hope for? And if we allow ourselves one more round, how does it help in reducing the query complexity? So there's a trade-off between query complexity and round complexity, and we would like to understand that. So the median elimination algorithm due to Evendar et al., which works for when k is 1, has query complexity n over delta k squared. This algorithm is for the fully adaptive setting, but it is possible to parallelize the execution of this algorithm and run it in log n round complexity. An extension of this algorithm is due to Kalyana-Krishnan and Stone, which works for any k and has roughly the same query complexity with an additional log k factor and roughly the same round complexity. And there are also matching lower bounds known for this problem, meaning that the query complexity of these algorithms is worst case optimal. But what about the round complexity? Can we reduce the round complexity of these algorithms? And the answer is yes. So our first result is an algorithm which achieves the same worst case optimal query complexity, but only uses log star n rounds of interaction. And this is surprising because log star n is a very slowly growing function, and for most practical n, this is just 5 or 6. Now, we again ask this question that, is log star n an artifact of our algorithm, or is it really needed? So our second result is that it is needed. Any algorithm that achieves the optimal worst case query complexity needs to have log star n round complexity. We also answer this question of trade-off between round and query complexity and prove almost matching lower bounds for any R round algorithm, lower and upper bounds for any R round algorithm. The only factor that depends on R is this I log R term, which is just log taken R times. Now with this introduction, I would like to discuss our results in a bit more detail. I will first discuss our algorithm, which we call aggressive elimination. Now, this is an elimination type of algorithm, which in each round eliminates certain candidates. It has two phases: the estimation phase, in which it estimates the bias of the candidate coins, and the elimination phase, in which it eliminates the candidates with the lowest biases. And the key difference is that its elimination becomes much more aggressive over the rounds. Here's a comparison of our algorithm with the algorithm of Kalyana-Krishnan and Stone. This is a plot of round versus the number of candidate sets in each round, and we can show that we can see that after round 1, our elimination strategy becomes much more aggressive and finishes in 4 rounds, whereas the other algorithm requires 16 rounds. So I'll illustrate our algorithm through 2 examples. The first example is a very simple example of a non-adaptive algorithm, a non-adaptive version of our algorithm. Suppose if we are allowed only 1 round and k is 1, and we have these bunch of coins. So in the first round, we toss each coin log n over delta k squared times. Let's say these are the empirical biases that we observe. So we now apply standard concentration inequality. This is empirical bias and this is true bias, and we get a very good concentration. So this picture is roughly showing that the empirical bias here can be used as a proxy for the true bias. So we just output the coin with the largest empirical bias. The query complexity is n log n over delta k squared. Now, one would expect the query complexity would be at least linear in n, but what about this log n factor? We can show that a 1 round algorithm needs this log n factor. You can't get rid of this. So can we allow ourselves 1 more round and maybe get rid of this log n factor, or reduce it to something better? So a 2 round version of our algorithm, in the round 1, we toss each coin log n over delta k squared times instead of log n over delta k squared times. We can again, so these are the empirical biases, we can again apply standard concentration inequalities like Hopdings and Chernoff, but we get a much weaker concentration this time, only 1 over log n. Now, so because we have weak concentration, some coins might jump over the top coin. Okay. However, we can show that there would not be a lot of them. there would be only a roughly 1 over log n fraction of the coins that would jump. And if we select the top 1 over log n fraction to go to the next round, we would not have eliminated the top coin. So in the elimination phase, we throw up everything and select the n over log n coins with the largest empirical bias. Let's say these are the coins. Now in the second round, where we have very few coins, so we can spend log n over delta k squared on these coins, and again use concentration inequalities to output the coin with the largest empirical bias. So the total query complexity is n log n over delta k squared. So we have reduced the log n to log n in 2 rounds. Now, extending this strategy, we can reduce, if we allow ourselves 3 rounds, we can reduce it to log n. And if we allow ourselves log star n rounds, we can completely get rid of the log n factor. So here is our main result. Formally, we show that our algorithm, aggressive elimination, finds the k most biased coins with probability at least 1 minus delta, where this small delta is the confidence parameter, using these mini coin tosses. Here again, this I log r is log taken r times. Now, this uses r rounds of interaction. If we set a value of r as log star n, we get the worst case optimal query complexity. Now, we also show a lower bound, proving that the upper bound is tight. And this is the main technical part of this work. So we show that for any nk, r, and delta k, we can construct a distribution on the instances of this problem such that any algorithm that outputs the k most biased coins with probability at least 3 by 4 and uses r rounds of interaction must have query complexity this much. Okay. As a corollary, we show that any algorithm that has optimal worst case query complexity needs to have round complexity at least log star n minus this very small additive factor. So note that this is very, very tight. So just to give an idea of the proof, for the case k is equal to 1, we show a minimax type of proof in which the adversary chooses one coin to have bias p plus delta uniformly at random, and all the other coins have bias p. So any algorithm which finds the most biased coin would have to identify which coin was chosen by the adversary. So the proof is by induction. We show the base case for one round algorithm. The induction is on R. So we show using information theoretic arguments that a one round algorithm requires this much query complexity. And as an induction hypothesis, we assume that any R minus 1 round algorithm requires this much query complexity. Okay. Now the natural thing to do is to show that any R round algorithm requires this much query complexity. Now the way we show this is that the way we show it is using contradiction. Suppose that an algorithm tosses too few coins, and in particular, if it tosses too few coins in the first round, then it can only narrow down its search to a relatively large subset of coins. Now, because this subset is very large, the problem still remains hard for R minus 1 round. So if the algorithm is still able to solve this problem, it will contradict the induction hypothesis. So I would just like to mention, in the interest of time, an application to ranking from pairwise comparison. Not have time to go into the details, but our algorithm shows some improvement over previous algorithms in terms of round complexity for the ranking from pairwise comparison problem. Now, to conclude, we propose the framework of limited adaptivity in the context of adaptive algorithms. We reduce the round complexity of k most biased coins problem from log n to log star n. while having retaining optimal worst case query complexity. And we also showed that log star n is tight. Now, as a direction of future work, we would like to study this problem for instance-wise query complexity. There has been a lot of work in the multi-arm bandit literature on instance-wise problems where the problem is parameterized by more gap parameters. Our algorithm already shows some improvement for this problem, but it is still not satisfactory, meaning that the upper bounds and lower bounds are not tight. And in general, we like this direction of, we would like to understand this trade-off between adaptivity and query complexity for other learning problems, other pack learning problems. This is all I have to say. Thanks.
Thank you very much. Other questions?
So can you repeat? Can you say a bit louder?
So I was wondering if you have a bounty on what you can do in one parallel round, like how does that come into play in the upper and lower bounds?
Yeah, it does come into play because it is the base case for the induction. Right? So we have an induction on R, or on the number of rounds.
Right, so I was wondering if you have another parameter for what can happen in a particular round.
In a particular round?
Right.
The algorithm is free to choose whatever it needs to. So we don't specify a bound on what the number of queries that the algorithm can make in a single round. And the algorithm is free to do whatever it wants to do over these R rounds. It can choose
so you don't know this trade-off, basically, like if there was a bound on that, on what you can do.
Yeah, it would be interesting to understand the problem if we have a bound on how many queries that the algorithm can make in a single round, but we currently do not have. And that is kind of enforced by the fact that the algorithm wants to minimize the query complexity overall.
Okay, thanks.
Yeah, so if you arrange the coins in sorted order of biases, it is the difference between the kth largest and the k plus 1th largest.
So, and you know this in the algorithm?
Yeah, so this is in the pack framework. So we assume that we know the gap.
Does it extend if you don't know?
Yeah, so you can, so basically there is a difference between worst case algorithms and instance-wise algorithms. So instance-wise algorithms are more adaptive, so they can adapt to the gap. And we can use RL, so basically the idea is you have to go from worst case to instance-wise if you want to adapt, like learn the gap. Yeah, it's very similar.
So an initial version of the algorithm that you have knows the gaps beforehand. In case of ranking with pairwise comparison.
Yeah.
But then you can sort of relax to the sun.
Yeah. So what you can do is so a lot of these instance-wise algorithms use this guessing type of trick where you initially guess this gap and
are the same bands hold it, or you have to pay something for that?
You mean the lower bound?
No, the upper bound.
Yeah, so you need to pay something in terms of the round complexity. You can't do it in log star n rounds. At least our algorithm wouldn't do it in log star, and you would require some dependence on the gap, worst case gap. Yeah, and that's the difference I was talking about.
Okay, thank you very much.